disks. Take this one, yeah, probably. Okay, yeah, thank you, Philip. So I'm going to talk about the recent work we've been doing in Copenhagen, and also with our collaborators, in particular Paolo Palwan and Veli-Matti Pelkonen, who is based in Barcelona. So we have this classical view of low-mass star formation, which it captures many of the aspects of how a star forms, but it's also a relatively isolated process where you start with an isolated core and create an embedded protostar that slowly consumes the core, and then it transforms or goes into the class 2, class 3 pre-main sequence stage where you roughly only have a disk, and this is where traditionally we think planet formation happens. But what we've seen in the past years, and also one of the large reasons why we are here this week, is that this classic view has to be updated because it's part of a larger multi-stage process where stuff is actually coming in from larger scales. We are also seeing that when we look at the small scales, at the disks with, for example, ALMA, there's growing evidence of structure even in very early disks. And this hints maybe that planet formation happens earlier, is more efficient than we originally thought. And therefore, if we want to understand planet formation, we also have to take into account this updated view of star formation. So star formation is going on in molecular clouds, and I couldn't help putting in this movie with such a large screen, basically showing a piece of the galaxy forming molecular clouds. So you can see they're very complex, filamentary, and along the filaments, and especially where they cross, you will have stars and groups of stars forming. Observationally, we've seen in the past years that this multi-scale process leads to mass coming in even while the star is forming. And here there are examples from all classes where you see these streams of material filaments that carry mass into the system while you have ongoing evolution of the star and the protoplanetary disk. So this is something I've been occupied with for many years now, and the tool I've used to try to understand this is simulations. Specifically, what we are using is adaptive mesh refinement simulations. For many years we used Ramses. Now we're transitioning into our own tool, Dispatch, that is still getting production ready, but has the great advantage that it's 100 to 500 times faster than typical Ramses and Flash models. So basically, we model a star-forming region, typically similar to Perseus, you can think, or low-mass local star-forming region. We have deep adaptive mesh refinement, so we can go to 25 AU resolution and look at the evolution over millions of years. On top of that, we can resimulate single systems with a zoom-in mode, where we concentrate all the CPU power on the resolution and can reach sub-AU resolution for up to 200,000 years. These are the examples you see here. Self-consistent binary system being built up. And over here, this is actually a dispatch simulation of a single disk showing streamers coming in. So that's the tool that we use to try to understand, interpret the observations better, and also build maybe better understanding of what's the effect of the environment and what are the dominating physical processes. We can compare it to observations and check things like the line width resolution, the line width relation, the morphology of the clouds we're forming, the density distribution, and see that it actually relates quite well to the observed phenomena. One of the key things we've been applying the past couple of years is using passive Lagrangian tracer particles. So what they do is that they follow the flow through the gas, and that way we can analyze where did stuff come from that ended up, for example, in a star or in a disk or in a core, what is the history of the material, and also recently, through careful analysis, we've looked at the angular momentum and spin in the system. So starting with where did stuff come from, here results from Pelkonen et al. 21, where we looked at the transport of a material. So basically we say, okay, the moment the stars formed, let's try to look at the gravitationally bound material. That's what you see here for high mass system, low mass system, right? And then the red tracer particles are the ones that are eventually being accreted onto the star, and the blue ones are the ones that never make it into the star. Maybe they become part of an outflow, maybe they just miss the core and are on unbound trajectories. But then when you zoom out and look at the accreted material, we actually find that even for low mass stars, a significant fraction of the material comes from quite far away. So that sort of points towards a new picture where you don't have an isolated core, not even for the low mass systems. Statistically, it's 50% of the material for stars less than 1 solar mass that comes from beyond a gravitationally bound core in this analysis. Instead, the star consumes the initial core, and while it does so, stuff is brought in. Now, we can also look at it in a time perspective. This is what we did last year. So here there are just two cases that sort of illustrates this diversity in the system. So one is an early case. So what we have over here in the figure is showing how far away in a cumulative plot does the material come from. So when it becomes flat, it basically means that there's no more material. And you see that in this case, you can also see it over here in the plot, in the figure, material basically confined to a well-defined core. This is our classical view, right? In another case, we see again that material is brought in from far away. So what are the consequences of this? Well, the consequences are that you have both an appearance, observationally, but also an evolution that is non-steady. And sorry for the very busy plots. So the upper two plots come from a paper that was accepted yesterday, very nice, where we look at zoom-in models, so highly resolved models with AU resolution. This is the single star. These three are binary systems. We see this pumped accretion both in the bolometric temperature. This is what is showing over here in this system here, in this plot here, from different viewing angles, especially when you see the system face on. You see large variations in the bolometric temperature, which means that the system can look like a class 1 and then maybe 1,000 years later look like a class 0 again, right? In terms of disk sizes, this is what we have over here. We see the same kind of periodic behavior, both for the primary and secondary disk, but also in single systems. And down here, this is the same plot for a single system. And this is actually from a paper. I don't know if you ever had these papers you spent years on, and you think it's the best ever, and nobody cites them. This is one of them. It's actually a very nice paper, and it discusses some of the issues that we are talking about this week. Here there's an example with the bolometric temperature. Well, the conclusion is bolometric temperature is a bad estimator of the age of the system. Now, another thing that this infall can do is change the orientation of the disk. So this was non-trivial to measure, but what we do here, this is global simulations, 25 AU resolution, so we can only look at the spin of the material that is falling onto the disk, okay? And what we find is that if we compare the spin of the star, so of all the accreted tracer particles at 1.2 megayears in time, even if you go to very low mass systems, you see a significant variation early on, then it settles down. If you go to high mass systems, you see large variations throughout the evolution. That points to that, especially for higher mass systems, one can expect to have changes in disk inclination, warps in the disks. Is there evidence for this? Well, we've seen a lot of scattered evidence. I think this figure was also showed yesterday. Recently came out a very nice paper by Valdivia Mena and collaborators, where they tried to look at objects in Perseus and find that, especially for the embedded objects, there are streamers associated with many of them. Now, finally, we have been looking at, you could say, more quiet accretion. So this is both theoretical but also analytical work that actually goes back to an idea by Paulo Padovan in 2005, namely that maybe both the accretion rate and the angular momentum in pre-main sequence, so class 2 disks, could be supplied by Bondi-Hoyle accretion. And what's done in the theory paper by Paulo is integrating for supersonic turbulence, for turbulent flows, what is the contribution in the angular momentum, both considering, say, naked disks and also embedded cores. And what we find is this two nice regimes that actually line up quite well with observations. So all these point observations, the disks are basically these two equations here. And we have a prediction, which is that with JWST, we should be able, just in 2-minute exposures, to see these Bondi-Hoyle tails if we go out and look for them in many different systems. These examples here are for the global simulation, where the analysis have been done. This is actually a very recent example from a zoom-in run, where I managed to evolve an M dwarf all the way to the class 2 stage, and you see the same kind of Bondi-Hoyle tail building up. So, lots of stuff, but I think one thing I will end with is just to say we have to be a little bit careful when we have discussed this. We have had a long discussion about the disk evolution for class 2 disks. Are they MHD wind-driven, or is it viscous spreading? And there's this very nice picture from Protostars and Planets. Maybe when we have infall, we can be cheated. Maybe it's MHD wind-driven, but with infall, it looks a little bit viscous. So also it points towards this, from another Protostars and Planet paper, this revised picture of low-mass star formation, where we have additional material coming in from the streamers, and at late times, episodic events from streamers for some systems, and also gentle infall from the low-density medium. So, environment matters, coming back to my starting slide, and to summarize, stars are born in turbulent, interacting media. In the early embedded stage, they're nurtured by nearby material, but stuff is falling in, while at later stage, you can both have Bondi-Hoyle and episodic events. Disks, they form early, but maybe be destroyed multiple times, change alignment. And I think one thing that is still in store for us is try to figure out what does this mean for the substructure in the disk and for planet formation. I will just take 1 minute more to show this beautiful movie from a recent dispatch simulation of a young protostar showing all the structure we see, at least in the simulations. Thank you.
Okay, thank you, Troels. So we can take questions while the movie is playing. We have time for 2 questions. We start with Patrick.
Thanks. Yeah, I really love the results about the bolometric temperature not being a good indication of age in the system, and I fully agree with that, and have done this on the observational side a little bit too. Do you have, since age is so important for things like planet formation and timescales for planet formation, et cetera, do you have any ideas for how to better characterize the age of these systems? I've been a proponent of trying to use more physical properties like envelope mass to disk mass or stellar mass, but of course, if there's late infall, that may not be a good characterization of age either.
It's a good question. I'm not sure I have a good answer to it. There may be some help if you look to binary systems. If you have wide binaries, we see this evolutionary trend where they start out very wide, very eccentric, and then slowly build up a circumbinary disk. That could be an indicator. I also think that given a mass of a protostar, and then look at the envelope mass, that gives you some indication of what stage it's in. But it's very hard not to crack.
Hi, thanks for the interesting talk. I want to know that how infall can change the disk orientation. I couldn't really understand that part when you were mentioning.
Well, to begin with, the infall from the core is more or less coming from all places, but it's the spin of the material is basically coming from this well equilibrated core, right? But at later times, when you have stream of material coming in, it may come in with completely different specific angular momentum, and that changes the alignment, because then stuff lands with different specific angular momentum. So that is particularly important for late infall.
I see. You mean the disk inclination can get changed over the time?
Exactly. This is what we see.
And how that can impact the YSO's eruptions, or does it impact, or can it impact, you think?
That's a good question. I'm not sure if there's a direct connection between misaligned infall and driving eruptions, but you could say the time dependence of the infall certainly drive eruptions. Another thing that also does it is binarity when you have eccentric orbits.
Okay,
thanks for your comments.
We're going to finish with a question from Zoom. Eleonora Fiorellino says, a very nice talk. Thanks a lot. I totally agree about the T-ball conclusions. I was wondering, what is the statistics of streamer results? 7 of 16 young stellar objects is 40%, but definitive conclusions with 16 sources are hard to believe. Also, what is the fraction of streamers detected in continuum on class 2 over the total class 2 of that region? Okay, it goes on, but I think we can...
Okay, many good questions I would like to know the answer to. We don't have the statistics in our models yet, and I think observationally this is what people are also pushing for. Yeah.
Okay, let's thank Troels again, and we're going to move to...